Hello and welcome back to my channel, and today we'll be talking about heat capacity. So let's do a quick refresher on what is heat, what is thermal energy, what is temperature. Just do a quick refresher. Well, thermal energy, which is really what this unit is about. Thermal energy is the total kinetic and potential energy added together, right? So they're the addition of the kinetic and potential energy. So that's what thermal energy is. What is temperature? Well, temperature is then the average kinetic energy. And an object or substance or whatnot. And finally, what is heat? Heat is a transfer of thermal energy. It's the transfer of thermal energy. So something we should focus on in this lesson is what is heat capacity? Well, heat capacity is basically, move over to the side here. Heat capacity is the amount of energy in joules, of course, that is needed, or amount of energy to increase the temperature of 1 kilogram of a substance by 1 degree, right? So the units for this are just joules over kilograms degrees Celsius. And the symbol we're going to be using is just going to be a C. So that's the symbol we're going to be using. Before we go further, let's take a look at this really like heat chart, or this chart here. And the uses for this chart is it tells us the specific heat capacity needed to heat up an object, how much energy is really needed to change the temperature on something. This is the heat capacity of each object. For water, you'll see that it has a very high heat capacity compared to ethanol or ice. And then you'll see aluminum, glass, and iron have even greater heat capacities. We'll actually need this chart to do some of the questions we have, because this gives us our C value, or our heat capacity. So we know what our C is. For water, our C is 4.18 times 10 to the 3 joules over kilograms degrees Celsius, and so on and so forth. We have everything labeled out there. So now let's look at what the quantity of heat means. So if we're talking about what the quantity of heat is, we're talking about the quantity of heat. The quantity of heat refers to the amount of energy transferred between two objects. And the symbol we're going to use for this is just simply going to be Q is equal to MC delta T. And M stands for the mass, C stands for our capacity. And then the final part about this is a temperature 2 minus temperature 1. And the units in this is going to be just joules. So now that we have all this and we understand this, we can look at a sample problem right here and try to use what we've learned and really apply it to the concepts here. So we can go into our given. So when a 200 milliliter when a 200 milliliter when 200 milliliters of water is heated up from 15 degrees Celsius to 40 degrees Celsius, how much energy is absorbed by the water? Something specific about water is that 1 milliliter of water is equal to 1 gram of water. And to go to kilograms, this only works for water. To go to kilograms from water, we can simply just divide by 1,000 and go from milli to kilo. This only applies to water as a substance. This does not apply to all substance as a whole. So now we can write the C of water, or the capacity of water, which is 4.18 times 10 to the 3. So 4.18 times 10 to the 3 joules per kilogram degrees Celsius. Then we're looking at the water is heated up from, so our temperature 1 is equal to 15 degrees Celsius, and our temperature 2 is 40 degrees Celsius. How much thermal energy is absorbed by the water? So we're looking for our Q value. So required to find Q. So now that we have that, we can go into the next part of our equation. So by delta T up here, when I put delta T, I realize that it could be confusing to what delta T we're talking about. Delta T does not mean before how we did delta T is equal to time. And this time when we're talking about delta T, we're talking about the change in temperatures. So T2 minus T1. That's what our delta T is. So our formula simplified is just equal to MC delta T, or Q is equal to MC T2 minus T1. That's something I thought I should clarify, because even looking at my formula right here, looking at this question right here, I thought about how it could be confusing, how I put delta T up there, and you're like, oh, why don't we have delta T or any of that? So that's just something to keep in mind. Now we can go into our analysis. We know that Q is equal to MC delta T, and Q is equal to MC T2 minus T1. And we can just go straight into our solution. So Q is equal to the mass. Remember we talked about how the mass of water, 1 milliliter of water is equal to 1 gram. So we can convert this from the mass right away. We can just go mass is equal to 0.200 kilograms, because 1 milliliter is equal to 1 gram of water. So now that we have the mass, we just go 0.200 kilograms multiplied by the heat capacity, which is 4.18 times 10 to the 3 joules per kilogram degrees Celsius, and then just multiply by T2 minus T1, which T2 is going to be 40 degrees Celsius, and we're going to minus that by 15 degrees Celsius. And now we have Q is equal to, and now from here, this is simply just calculator work. We can punch this into our calculator, and you should get 20,900 joules, and we can simply just put this into kilojoules to lower our digits. And if you notice, we have 2 significant digits here, so we should round off to 2 significant digits. So you'll get 21. Well, you can write it as 21 kilojoules, because you should get 21,000 when you round off, and then divide that by 1,000, and you get, 210 kilojoules. I just want to make sure my units are correct. I'm just looking at this another time. But in the end, if you want to really just leave it as joules, it's just 21,000 joules, or 210 kilojoules. Okay. From here, we can go into the next part of this video, which will be thermal energy exchange, and we'll talk about what the principle of thermal energy exchange is, and we're going to apply it to some more practice problems. Okay, now let's talk about the principle of thermal energy exchange. So what are we talking about when we're saying the principle of thermal energy exchange? Well, this basically means when a warmer object touches a cooler object, heat it loses is equal to the heat the cooler object gains. So if you think back to what we talked about in energy, this is similar to the concept we were talking about in energy, how energy is not lost nor whenever we do a transfer, it's not created or destroyed, it's always conserved, right? So the same kind of principle, I guess, applies here when we're talking about heat. If we take a hot object, the heat's just going to transfer over to the cooler object. We're not going to lose any heat in the process of doing this. So the equation we're going to use for this is, we can name it like Q released. So the quantity of heat released is equal to the negative of the quantity absorbed. What you label these are really up to you. You can label it whatever you want as a subscript, but this is just what I chose to label them as, which is just equal to QR is equal to QA. So negative QA. So that is the formula we're going to use, and we already defined what Q is up here. In case you forgot, remember, Q is just equal to MC times T2 minus T1. So now that we have that, let's look at a practice problem that we have down here using this principle of thermal energy. So let's get into our given. Given a 60 kilogram sample of metal is heated up to 100 degrees before being placed in a 200 milliliter before being placed in 200 milliliters of water with an initial temperature of 10 degrees. Together they reach a final temperature of 15.6 degrees. What is the metal? Okay, so we're looking for the heat capacity, right? We're looking for what the metal is, and to determine what the metal is, we have a chart up here, remember, with the list of metals. So if we can find the heat capacity, we can in turn basically find out what metal it truly is. So how are we going to do this? There's a few things we can do here to try to determine what it is. So the first thing is a 60 kilogram sample of metal is heated. So we don't know what that metal is, but we know that it's heated to 100 degrees. So the T1 is going to equal 100 degrees Celsius. So we have that. Now we're looking for before being placed in 200 milliliters of water. So we know that the weight, the mass of the water, remember 1 milliliter is equal to 1 gram. So the mass of the water is 0.200 kilograms, and we have the weight, so we have M2 and we have M1 as well, which is 0.06 kilograms. Now that we have that, it says the initial temperature of the water, so T2 subscript 1, or no, you don't really necessarily need to put that. You can put T2, you can put T1 1 and then T2 1 just to differentiate the two. But how you really subscript them is really up to you. This is how I chose to subscript them, but it really does not matter. I just put T2 1 and then T1 1, but it doesn't really sorry about that, but it doesn't really matter again how you label them. Now we know T2 1 is going to be 10 degrees Celsius. Actually, a better way of labeling them would be putting what they are. So we can put M1 metal 1 and then water 1. That's a better way, I believe, to label them. And then that says that together their final temperature is 15.6 degrees Celsius. So their final temperature is the same for both. So we know that the final temperature is going to be for T metal is going to be 15.6 degrees Celsius, and T water is going to be 15.6 degrees Celsius. Now that we have that done, we can go into our required to find. We're looking for the heat capacity, so we can find out what metal it is. So let's get into our analysis. So we can, the first thing we can do is we can go QR is equal to negative QA, and now we can sub in what it is. So MC T, we can put, we can change these to metal, for metal, and M2 we can change to MW, mass of the water, just to keep everything linear. So we can put metal. So we can put right here when we go QR, which is the one that's being absorbed. Because remember, how do you know which one's QR and what's QA? Well, the sample of metal is being put into the water. So we know that our water is going to be the second substance. Because our initial substance, or our first, is the metal being put in. So now that we know that, we can just go, pardon me, let me just rewrite this here. So my QR is equal to negative QA. So we know it's going to be MCT, well, technically we should put MC and put T2 TM2 minus TM1, and this is equal to negative C MWCW. You can put CW as well. It's probably better to keep your subscripts all the same, really. And we can leave this negative hanging up front for now, and then we can put T2 TW2 minus TW1, and we can divide that out again by pardon me, you don't divide anything, but that's what we have so far. You can either distribute this negative in already, or we can just wait till the end. For right now, I'm just gonna wait till the end just to keep it a little simpler, but it doesn't really matter. Also, we can go ahead and put the C for water right now, just because it'll be better. So it's 4.18 times 10 to the 3. So 4.18 times 10 to the 3 joules per kilogram degree Celsius. So now that we have this, we can move into actually solving, because we're kind of isolate for CM, right? We're looking for CM. So how are we going to do that? We're just going to divide by MM, and we're going to divide by the brackets. So now we're left with CM is equal to negative bracket. I'm going to put a big bracket right there. Negative MW times CW, subtract TW2 minus TW1. And their TWs are really the same, so you can, they're the same final temperature. They're used to the same final temperatures, so it doesn't really matter, but it's something to keep in mind. We could factor it out if we really wanted to, but I just want to keep it simple, so we can just leave it in, and we're dividing by the brackets, so it's going to be TM2 minus TM1. Now that we have this, we have CM by itself. From here, it's just simple. We can just simply go straight into our solution. So CM is going to equal to negative, and then we're going to go MW, which was mass of the water, which is 0.200 kilograms, multiplied by CW, which is the heat capacity of the water, so 4.18 times 10 to the 3 joules per kilogram degree Celsius. Oops, I put that degrees, sorry. Degree Celsius. From here, we can go into, pardon me, we can go into multiplying by the brackets. So our TWs are going to be, so the temperature 2 was a final temperature of 15.6 degrees Celsius, and we're subtracting the first temperature, which in this case was 10 degrees Celsius, as stated right here. And then we can close off this bracket, and then we're going to divide by mass of the first, mass of the metal, which was 0.060 kilograms, and we're going to multiply that by the brackets, which is, so our initial was 100 degrees, pardon me, our final is 15.6 degrees Celsius, and we're minusing that by 100 degrees Celsius. And now we can go ahead and really just put in our numbers. Pardon me, we can just go ahead and put it into our calculator if we'd like. And this, you'll notice this will actually end up being a negative right down here, but because we have a negative up top, they'll cancel out, and you will be left with 9.24 times 10 to the 2 joules per kilogram degrees Celsius, and that is our final answer. Now that we know what the heat capacity of the metal is, now it's just a matter of going up and trying to find out which one matches it. And 9.24 is really close to the heat capacity for the aluminum, which is just 9.2 times 10 to the 2. And if you go down here, that's exactly what we have. So we can just assume that this is being placed in this container. For this unit, it's really just about understanding that energy, again, or thermal energy is not lost. It's just about being able to collect like terms. Here, you really could have collected TM2 and TW2 just because they're the same. You could have collected that out, and you could have done a lot of things here that would make this quicker. You really want to make sure that you distribute terms inside the brackets as well, because here it was simple because we could just divide by the brackets and divide by m, but really what you should be doing is distributing in and then dividing. Sometimes you will have to distribute then divide. Here it just kind of worked out that you didn't really need to, but that really won't always be the case. But now that we understand that, that's basically all I have for this video. You just want to really make sure that you remember that these are two separate terms that you have to divide, they have to multiply into the brackets sometimes to expand out the brackets. Sometimes you'll be lucky you don't need to expand, but in other questions you will need to expand. It's just about going through your fun work and just looking for when and where you have to and when and where you don't. But that's all I have for this video. I hope you enjoyed the video, and remember, physics rocks.